In the early 1920s, Detroit, Michigan, and Windsor, Ontario had a growing problem. Both cities were riding the boom of automotive manufacturing. Factories were expanding and jobs were growing, and traffic between the two sides of the river was growing as well. But no matter how closely the two cities were tied together, there was still one thing in the way: the Detroit River. Now, ferries had handled this crossing for years, but the demand had become so great that the entire system was struggling to stay afloat. A permanent fixed crossing could no longer be ignored. By 1928, one was already being built farther south, the Ambassador Bridge. It would give the region a permanent way across the Detroit River, but it did not solve the city-to-city problem at the heart of Detroit and Windsor. But the downtown landscape couldn't provide the room for bridge approaches for a high river clearance. Instead of going over it, they would go under, setting the stage for several cutting-edge technological advances designed by the same superstar team behind the world's first automobile underwater tunnel. And in the process, it would make this structure one of the very first to widely use electric arc welding as a reliable tunnel construction method. Well, my name is Scott, and today we're taking a look at cutting-edge tunnel technology. At least it was in 1929, and it still remains the only underwater automobile international crossing in the entire world. This is the Detroit-Windsor Tunnel. Let's go beyond the exit. Today, the Detroit-Windsor Tunnel doesn't really feel like something that should have been impossible. Its two-lane width and white tile walls often make the passage feel like an antique in the modern age. My personal experience from driving it in 2018 was similar to traveling through some of the older sections of LAX Airport, more of a historical review rather than a technological exhibit. Its entrances and exits are also not as dramatic as its southern neighbor, the Ambassador Bridge. There's no grand view from the top and no towers rising over the skyline. There's no long climb above the ships. The tunnel does its work by hiding almost everything that makes it remarkable. And that's why it makes this story easy to miss. Because the crossing people drive through today was a revolutionary engineering answer to a problem hiding in plain sight. Two cities close enough to see each other across the river, but too busy to keep working around it. The real story is in the details: how it was built, for when it was built. The engineering responsibility went to Parsons, Clapp, Brinkhoff, and Douglas, the same firm behind the Holland Tunnel. Detroit-Windsor was not being handed off to a road crew learning its way through a river crossing. It was being put in the hands of tunnel engineers who already understood that an enclosed automobile crossing had to be designed as a complete working system. And in this case, they didn't hire just anyone. They hired the superstars. Now, to understand where they were building, picture the tunnel as a line just short of a mile long, running from downtown Detroit near Jefferson and Randolph to downtown Windsor at Goyot Street. But that line didn't have the same problems end to end. On the Windsor side, the approach could slope down in a fairly direct line toward the river. On the Detroit side, there was not enough open land for that, so the road had to descend in a spiral before it could aim for the crossing. Three separate tunneling methods were used on the Detroit-Windsor Tunnel: open cut, shield driven, and trench and tube. All three began almost simultaneously, mainly because each section had to be completed on a schedule tight enough for the pieces to meet underground. Now, at both ends, the roadway had to leave the city street, so crews used the most direct method available. They opened up the ground, dug down, built their concrete structures in place, and then buried it all again, hence the name cut and fill. Now, closer to the river, the problem changed. The roadway still had to keep moving downward, but now the crews were working through riverbank clay and wet ground. This is where shield tunneling came in. A massive steel shield was pushed forward through the earth, kind of like a giant cylindrical pastry cutter, driven forward with hydraulic jacks. It would extend a few feet at a time, allowing the workers, called sandhogs, to safely enter and muck out the debris, placing it in small mining cars to be removed from the shaft. Now, in traditional tunnel building, the shield method during this era would have been used to go horizontally under the riverbed. However, due to the shorter approaches, the tunnel needed to sit at a shallower depth in the river. So, since they couldn't create the tunnels underground, they'd make them on shore instead. The decision was made to try something unique. Giant prefabricated tubes. 9 were fabricated in total, with each section reaching nearly 250 feet long and about 31 feet across. The shell began with steel plate that was 3/8 of an inch thick. They were fitted into place and stiffened with octagonal steel collars inside and outside the tube, then either welded, riveted, and tested for water tightness before the tube ever left the shore. Now, one of the most advanced parts of the work was hidden in the seams. The project used roughly 65 miles of electric arc welding, the first major use of arc welding in tunneling history. Before launch, both ends were closed with heavy timber bulkheads that were backed by steel trusses. They were sheathed for water tightness and covered with multiple layers of waterproofing. Concrete was poured along the bottom, adding weight and giving each tube a keel of its own while it floated downriver. A launch canal was dredged along the shore, and wooden runways were built so the completed steel sections could slide into the water. The only problem is, it didn't. Tube A was released, but the canal had not been dredged deep enough. Instead of floating free, the tube just settled into the mud. In a frenzy of activity, crews dredged deeper and built several wooden pontoons that were hollow inside. These were all sunk and attached to the tube itself, and then the water was pumped from them, and the buoyancy allowed the tube to break free. Once it was afloat, the section was towed into a deeper slip for the next stage. Forms were built around the sides and tops, and reinforcing steel was placed as well. Concrete was poured into the interior walls, the exterior encasement, and the roadway structure. When that work was finished, each tube was surrounded by concrete roughly 3 to 3.5 feet thick. With all the additional weight, it became an 8,000-ton monster that was actually still buoyant enough to be floated into place. As you can imagine, the launch of the next 8 sections went much smoother. By 1929, the Windsor Shore had become something closer to a shipyard than a road project. But before any of the tubes could be towed into place and sunk, the Detroit River had to be prepared to receive it. That meant cutting a trench completely across the river bottom from shore to shore, long enough and accurate enough for 9 separate tube sections to meet end to end and be properly aligned and sealed. The trench itself was 2,454 feet, and the dredges removed roughly 700,000 tons of material from the river bottom. At its greatest depth, the trench reached about 85 feet below the river surface. It was roughly 20 feet wide at the bottom and 90 feet wide at the top. The dredging cut the trench, but it didn't create the final seat for the tubes. Before the first section could be lowered, crews placed a sand bed in the bottom of the trench to bring the grade to true. Engineers built a leveling machine for the river bottom. It used a hollow rectangular steel raft with rails that were mounted on pontoons and a carriage that moved back and forth like a screed. As the carriage traveled across the trench, it swept the sand into grade. With the trench dug and prepared, all that was left was to move the tubes into place, hold them against the river current, and drop them perfectly, side by side, into the bottom. For the sinking operation, tall guide masts were fastened to the end of each tube so engineers above the water could track the position of the section below. Then crews changed the tube's weight by adding concrete blocks a little at a time to slowly sink the tubes into place. The final tube section itself was nearly the hardest to place because it was almost as deep as the river itself, damming up a considerable amount of water. To hold it in place, 25-ton anchors were set at the river bottom, attached to it, and 3 powerful tugboats pulled against it as it was lowered into place. Once the section was down, the final connection moved to the divers. In dark water, divers fastened each new tube to the one already in place with heavy steel lug pins. Steel forms were set around each of the joints, and concrete was poured underwater through tremie pipes. That sealed the outside connection before the timber bulkheads inside could be removed. In the final step, the clay that had been dredged for the trench was placed back over the tube with additional material to cover it properly. Now, completely covered and in place, the main tunnel passage would have to wait for the sides to meet it. As we mentioned earlier, shield tunneling drives a gigantic cylinder slowly through the muck, providing a protective shield for the workers to remove the material. To say it was a difficult job would be a complete understatement. These brave men, known as sand hogs, worked in a high air pressurized environment, required to keep the existing tunneling from collapsing on them. Because the shield chamber was kept under compression, the men could not simply step out at the end of the shift. They had to come back through an airlock and return to normal pressure gradually. Otherwise, they were exposing themselves to decompression sickness, also known as the bends. It was very slow, tedious work. Remarkably, all the pieces met under the Detroit River was less than an inch of error, a pretty remarkable feat even by today's standards. Once the river tubes, shield sections, and land approaches were joined, it was time to begin on what would become the roadway. Inside the tube, crews paved the roadway with about 2 million granite blocks. The walls were finished with more than 200,000 enamel porcelain tiles, giving the enclosed roadway a hard, washable surface that reflected light through the traffic space. Now, the portals needed their own infrastructure. This was an international crossing, so the tunnel could not simply rise out of the ground and empty into the city streets. So in all, about 25 buildings were constructed around the tunnel entrances, including service spaces, control rooms, power, drainage, and ventilation systems needed to make the tunnel function every day. But strangely enough, one of the oldest fears about an automobile tunnel was still waiting inside the finished structure. People had worried for years that a long enclosed roadway would not just trap traffic under a river, it would trap the exhaust with it. And that fear led directly to the next engineering problem: ventilation. Thankfully, in New York, a solution had already been put into place. That is where Ollie Singsted's tunnel ventilation work came into the story. Instead of relying just on natural draft or trying to force cyclonic speed winds through the tunnel, fresh air was forced into the tunnel under ducts below the roadway. It then passed through the traffic space near the curb, and that air draft, along with the exhaust, was pulled above the ceiling. Ventilation towers drew air from near the surface of the river and exhausted it at each end. In fact, it was such an effective system that it could turn over the entire atmosphere of the tunnel every 90 seconds. And finally, with all the construction completed, on November 1st, 1930, crowds gathered on both sides of the Detroit River for the dedication. President Herbert Hoover took part, albeit remotely, from Washington. 2 days later, traffic began moving through the new crossing. For Detroit and Windsor, the change was monumental. A trip that once depended on ferries, weather, and ice, not to mention river conditions, now had a fixed path below the water. And it made a complicated international border crossing feel ordinary. But most of that feeling was simply because most of the work stayed out of sight. To man the tunnel today takes over 100 full-time employees working 24 hours a day, 7 days a week, watching security cameras and responding to breakdowns, maintaining ventilation and managing water intrusion, not to mention washing walls and inspecting systems, and of course keeping traffic moving through a structure that is now approaching a century old. As you can imagine, several upgrades had to be rebuilt around the original machine. A $50 million renovation took place in 1993, which upgraded the road's surface, including sidewall tile, lighting, and video surveillance. In 2006, another $25 million modernized the ventilation system. By 2018, a $30 million ceiling renovation had been completed as well. And just like any structure, it can't simply be left alone. And that's the part of this system that most drivers never see. At nearly 96 years of age, today it's estimated that nearly 12,000 vehicles a day, or a little over 4 million vehicles per year, passes through the tunnel, nearly 98% of it passenger vehicles. With that much time and that many people, there have to be hundreds of stories waiting to be told about it. Maybe you'd like to tell us your story. We'd love to hear it in the comments, and we take it very seriously, trying to answer nearly every comment we receive. In fact, we like stories so much that we're going to be doing a special episode coming up here in early June, sharing some of those with you. We'd really appreciate it if you go ahead and hit that like button right now, or maybe even share it with a friend, because it goes so much further on YouTube when you do that. Here at Beyond the Exit, we are a little bit different, mainly because we believe the highway should be the hero of each of our stories. If you like that too, why don't you join us in our BTE caravan? You can do that simply by subscribing to the channel, and it's absolutely free. We know that YouTube also can be a pretty daunting landscape to find your way through, so the fact that you came beyond the exit with us for a little while means a lot. As always, thanks for watching, and God bless.